Good day, Bayaus. Today we're going to solve a problem from the book of Thermodynamics by Eunice Engel, Chapter 6, Vapor and Gas Cycle. An ideal Otto cycle has a compression ratio of 8. At the beginning of the compression process, air is at 95 kilopascal and 27 degrees Celsius, and 750 kilojoules per kilogram of heat is transferred to air during the constant volume heat addition process. Using constant specific heats at room temperature, determine the pressure and the temperature at the end of the heat addition process, the net work output, the thermal efficiency, and the mean effective pressure for the cycle. So first is we're going to identify the given wherein our pressure 1 is equal to 95 kilopascal, temperature 1 is equal to 27 degrees Celsius, and we're going to convert it into Kelvin and we will get 300 Kelvin. Our compression ratio is equal to 8 and our heat in is equal to 750 kilojoules per kilogram. So going back to the problem, air is mentioned, and if we're going to look at it in a property table, table 8.2, the air's constant pressure is equal to 1.005 kilojoules per kilogram times Kelvin, and the constant volume is equal to 0.718 kilojoules per kilogram times Kelvin, and the specific heat ratio of the air is equal to 1.4. So step 1 is the process 1 to 2, which is our isentropic compression. We're going to find the temperature 2 and the pressure 2 since it is not given. So if you guys didn't know, temperature 2 over temperature 1 is equal to volume 1 over volume 2. So since here we're looking for the temperature 2, we're just going to cross multiply it to get this equation, wherein our volume 1 over volume 2 is equal to the compression ratio. So with this equation, we can now find our temperature 2. So just substitute all the given value and we will get 689 Kelvin for our temperature 2. Next is to find our pressure 2. We're going to use the combined gas law equation. So since pressure 2 is what we're looking here, we're just also going to cross multiply it to get this equation. So as what I've said earlier, our V1 over V2 is our compression ratio, which is 8. So just substitute the given value here and plug it in your calculator, and we will get 1,745 kilopascal for our pressure 2. So next is the process 2 to 3, constant heat addition. We're going to find the pressure 3 and the temperature 3 here since it is also not given. We're going to use this equation wherein our specific heat in is equal to internal energy at state 3 minus internal energy at state 2 is equivalent to constant volume times the quantity of temperature 3 minus temperature 2. So if you guys are wondering where did I get this one, just look at in the table wherein our change of internal energy in process 2 to 3 is equivalent to constant volume times the quantity of temperature 3 minus temperature 2. So with this equation, we can now find our temperature 3. So just substitute all the given values and plug it in your calculator and we will get 1,734 Kelvin. So next is we're going to find the pressure 3 using still the combined gas law equation, wherein our volume 1 and volume 2 will be cancelled. Since if you're going to look here in the process 2 to 3, our volume here is constant, same with the state 4 to state 1. So with this equation, we can now find our pressure 3. So just substitute all the given values and plug it in your calculator and we will get 4,392 kilopascal. Next is the process 3 to 4, isentropic expansion. So we're going to find here the temperature 4. We're not going to find the pressure 4 here because we don't need it in process 4 to 1. So with this equation, we can now find our temperature 4. So just substitute all the given value and plug it in your calculator and we will get 755 Kelvin. Next is our process 4 to 1, constant heat rejection. So we're going to find here our network and the specific heat output. So specific heat output is equal to internal energy at state 1 minus internal energy at state 4, which is, if we're going to look at the table, our change of internal energy in state 4 to 1 is equal to constant volume times the quantity of temperature 1 minus temperature 4. So that makes our equation like this. So with this equation, we can now find our specific heat output. So just substitute all the given values and plug it in your calculator and we will get negative 326.69 or negative 327 kilojoules per kilogram. So now that we have the specific heat output, we can now find the net work, which is equal to specific heat in, which is equivalent to 750 kilojoules per kilogram, minus the specific heat output, which is 327 kilojoules per kilogram. So just plug it in your calculator and we will get 423 kilojoules per kilogram. So now that the pressure and temperature at the end of the heat addition process and the network output has been determined, we can now find the thermal efficiency of the auto and the mean effective pressure. So what we're just going to do here is just substitute all the given values in the equation. So next is to determine the thermal efficiency of the auto, which is equal to 1 minus 1 over compression ratio raised to specific heat ratio minus 1. Just substitute the given values and plug it in your calculator and we will get our thermal efficiency of the Otto cycle is equal to 0.565 or 56.5%. Next is to find the mean effective pressure. Using this equation, mean effective pressure is equal to net work over the volume 1 minus volume 2 or net work over volume 1 times the quantity of 1 minus 1 over compression ratio. So you can use either of these two equations, but we're going to use this one here. So since volume 1 is not given, we're going to find it using the ideal gas equation. PV is equals to MRT, where the M is equivalent to 1. So it will become PV is equals to RT. Manipulate this one to get this equation for us to find the volume 1. So since our gas constant and temperature 1 and pressure 1 is given, we're just going to substitute it in the equation and plug it in your calculator and we will get 0.906 cubic meter per kilogram. So now that we have the value of our volume 1, we can now find our mean effective pressure using this equation, wherein our net work is equal to 423 kilojoules per kilogram over our volume 1, which is 0.906 cubic meter per kilogram, times the quantity of 1 minus 1 over our compression ratio, which is 8. Plug it in our calculator and we will get 534 kilopascal. So take note of this conversion, wherein our kilopascal times cubic meter is equal to kilojoules. So if we're going to cancel the kilogram here, the unit will be left is kilojoules per cubic meter, which is equivalent to kilopascal. That's why our unit here is kilopascal. So that is all for today's video. Thank you for watching.